In today's edition of Mechanics of Materials, we're going into the wonderful world of energy methods. So you can kind of think of this as being analogous from your physics and your statics physics classes when you did like forces. This is for a while, and you're in that wonderful world. And then the question came, well, is there another way to get some of the answers that are otherwise difficult to obtain with forces? For example, like you have things that depend heavily on time, right? Force is equal to the mass times acceleration. So if you have like an impact, that's kind of hard to model because you have some sort of impulse, and that's going to change with how long the things in contact and all that kind of garbage. Or like you have something falling, and if you want to actually know how fast it's going at the other end, you have to integrate and all that jazz. Or you could just do some sort of energy method where you just have a path length, you have a couple of forces acting on it, and time doesn't matter. And it's super useful, right? Because you can do all kinds of stuff. You can make all sorts of relationships, and that's kind of the angle that we're looking at it from. Being able to apply energy methods in a similar kind of through a similar kind of vein to how materials break or deform is really quite useful because you don't have to worry about certain things such as time delays. You can just compare scalar quantities to one another and say, will this fail based on how much energy this thing had, and this impactor say had, and how much energy this material can absorb before breaking. So that's kind of where we're looking at it from. And these are just two examples of kind of quintessential problems that you might be able to approach with this. One being this be a commercial turbofan that had a run-in with a bird, really large bird, and don't be mistaken. These are actually stubs. They aren't fan blades. The next fan blades are behind the disc. Those are actually all broken off. There are actually only 6 blades remaining on this front section in here because of just a bird coming in, hitting one blade, but then as soon as that one blade breaks off, it deforms the entire cowling, which scrapes all of the other blades and scrapes all them off. So it's a very dynamic environment that, if you wanted to analyze from a force perspective, I mean, all this happens on the order of microseconds. It'd be very difficult to actually quantify it, but you can quantify it from an energy point of view. If you think of it in terms of like rotational energy or kinetic energy, that you can quantify it by. So that would be one relatively straightforward implementation. The other one that I thought was really wild is that this might look like that's like a pipeline sort of thing, and this was a pipeline at one point. This whole thing was round. If you ever heard of water hammer before, this is kind of like water hammer in reverse. Your more traditional form of water hammer is that you have some closed system and you have some water rushing down and it slams into a wall, essentially. And because water is incompressible, your pressure can build dramatically over a very, very short period of time. But again, you have that period of time, and based on that amount of time, your impulse is going to change, right? So the effective force felt by the wall is going to skyrocket dramatically based on what time interval that is. Conversely, you could have what you call it. So you could also do that in reverse, where say like you had a pipe and you closed a valve here, which you might want to do in order to slow down flow, or there's a leak somewhere or whatever. You close a valve here, the fluid keeps moving through the pipe because it has some momentum, substantial momentum, because you're talking about thousands, if not millions, of gallons of stuff, right? And as it pulls away from that valve, there's nothing filling in the empty space behind it. So you just get a vacuum forming. And eventually it can get strong enough to actually crush stuff. I think this example is from a water pipe to a town. The pipe actually crushed when someone closed a valve upstream, and the town didn't have water for like a week or so. Come down the pipe because vacuum crushed it. Now, if you remember, pressure and volume can do work, right? And work's related to energy. So again, instead of having to worry about time delays and stuff, we can compute some sort, we can compute the amount of work being done and translate that into stresses on the material here. So just some kind of neat and kind of wild applications, at least for me. So let's have a look at this. So if you remember Hooke's law back in the good old days when it was just Hooke's law and it was a spring and you didn't have all this Poisson ratio crap to worry about, it was that F equals kx, right? You just have some, it's just back in the days when k is your spring constant, x is your displacement, and you get some sort of force, right? And if I plotted it, it would look like that. And if I integrated that, I could get like an amount of energy required to stretch a spring a certain amount, right? And I'm sure you guys have done like a billion problems where you have a weight dropping onto a spring and someone asks you, hey, if it has this much potential energy, how much does the spring compress, right? We've done like a billion of those. So I just wanted to draw a parallel again that materials are essentially springs. They're just big, fat springs, things that don't look like if it's called like a rubber band, you could model using F equals kx, right? Like you could model that with the more simplified Hooke's law. But remember that this is just a material. This rubber band has some modulus of elasticity. It has some Poisson's ratio. It has some yield strength. Right now, I'm causing a strain in the material. I'm creating a normal stress in the rubber band. I'm not exceeding its yield stress because it goes back to its undeformed length. But all materials fundamentally act in the same way. Like I have a rotor blade here. I can bend it, so it's acting like a spring. Again, it's some modulus of elasticity. I put some force in according to that stiffness, according to that modulus of elasticity. It's going to deform a certain amount, just like a spring or a rubber band would. And the same goes for everything. I mean, you just might not be able to see this thing deforming as I'm pulling because it's a steel bolt, but it is. It's just deforming by a very, very, very small amount. So what I'm trying to say here is that springs and everything else in the entire world that we can analyze as a material operate in more or less the same. Oh, bother! I hope this goes back. Operate in fundamentally the same way. Unfortunately, that same thing does not seem to apply to smart boards. We're getting there though, or so I hope. There we go. Okay, so sweet. And that's what happens when you close a smarting file. There it goes. So we're gonna follow the same sort of track in trying to apply energy methods ourselves. So say that I have a rod and I pull on it. I'm creating some form of normal stress, right? If I have some load that I'm applying to the end of the rod here. It has it's called. I'm saying that the rod's fixed on this end, so the load's getting transmitted from one end of the rod to the other. Like if I had if I had this ruler here, and if you grab the other end and pull really hard, thank you. If any part of this ruler was missing, the load would not be transferred from his hand to my hand. And all this material transmits the force between our hands. Thank you. So that means that there's some internal load, and if there's some internal load, it means that there's a stress. So that means that we can draw plots like this, where we look at internal load. In this case, it's just an internal force versus how much the thing's stretching. All right. So this is kind of like the same thing as our plot from before, right? If I had my spring, and I have some force, I have some displacement, I can draw a line, right? And I can say, hey, look, F equals Kx, because this is a straight line up to a point, right? Well, really, that's just the first part of this graph, right there. And that's where we said, well, sigma equals E epsilon. Stress equals the modulus of elasticity times strain. Now, what was the limit on that? When does that equation become invalid?
When it goes past the yielding stress point.
Right. Why?
Because then it starts to strain disproportionately.
Yeah, it's called after your yield. Strain no longer varies linearly with stress. It does some other very nonlinear thing. And that's why Hooke's law is only good up to a certain point. That's why he in physics lab, your lab instructor always said, and now don't put too much weight on this thing because it's going to break or something, or you get bad data or something like that, because the spring is going to actually yield at some point. That's when Hooke's law becomes invalid in either form. But anyhow, so if we so over that interval, it's relatively easy to integrate. But just as a more general thing, just the same way that we integrated F equals Kx to give us like the potential energy in a spring as 1/2 Kx squared, we can do the same thing to integrate and find the total amount of strain energy, if you will. So the amount of energy put into strain a material by integrating a load versus displacement curve for any given material, not just springs. Since work is F dot dx, so it's called a force times a parallel displacement. So like if I put a force on this and it pulls out in the same direction as that force, I can add up all the how do I want to say this? If I put in a certain amount of force, and that gives me a certain displacement, it takes a certain amount of energy to do that. And if I increase that force by a little bit, that gives me a little bit more her displacement, and it requires a little bit more energy to do that. And if I add up each incremental increase in force and displacement, and thus the amount of each little amount of energy that it takes to increase displacement until failure or some other point, that'd be like an integral. And that's where we get this guy from, which is an expression for strain, which is the general expression for strain energy, or which is called the integral of P, some force times whatever's her differential displacement that causes. All right, if you add all those up from 0 to wherever you want to strain to, or wherever you want to displace to, that would give you like a strain energy. All right, we on board so far? Yes, no, too early in the morning to respond? Okay, fair answer. All right. Oh, oops, need to get rid of you too. All right. So, game on. So if we have some expression for strain energy, that's nice, but it would be nice if this was in if this is in terms of like stress and strain, not load and displacement, because we don't usually work with load and displacement. If we want to relate energy stuff to stress and strain, we need to get it in terms of stress and strain. So know that a stress fundamentally is a force divided by an area, right? It's some force distributed over an area, and a strain is some change in length divided by a length, right? So this would be like a change in length, and that's a force. So we need to divide that. So we need to get a cross-sectional area in underneath that. So we need to like divide that by cross-sectional area. And we need to divide this by length. And if we're dividing both, if we're dividing by each of those things, it also means that implicitly they have to be multiplied by each other, right? And if I multiply those two together, what would I get? Volume, right? So let's divide this whole sucker by volume, where V is volume, not velocity or anything else that it's meant. All right, so if I do that, there's some U per V, actually make that a lowercase u. Lowercase u we'll call strain energy. Uppercase u is going to be something else. So you get like a strain energy per volume. Because volume's a constant, we can just move it in, we can move it into the integral. And we get some normal stress in the x direction times the differential strain in the x direction. And we call this big U, or strain energy density. Kind of like mass density is mass per unit volume. You get strain energy per unit volume. It's the strain energy density. Cool. So that's nice. Side am I on again? Sorry. It's 4. Okay, cool. All right. So this can be a nice thing. And if I keep that sort of an integral, I can take that and integrate over a stress strain curve now, and say that I integrate from 0 strain to whatever strain you have when the thing catastrophically fails. This would be like this would be around the ultimate strength of material. I could find the strain energy density that would, oh, I made this backwards, didn't I? Sorry. Big U is strain energy, little u is strain energy density. Sorry. Should follow my slides. Yeah. Small u strain energy density, big U regular strain energy. Sorry, I got them reversed. But get back to what I was saying. If you integrate that across the whole stress strain curve until you hit rupture, you can actually get kind of the strain energy density of a material when it fails. Now, say that I recast my my integral, which was like that, in terms of epsilon. I can I can integrate that and end up with something like this. Sigma squared over 2 times the modulus of elasticity. And if depending on what I substitute in for that stress, be it the ultimate stress or like the yield stress, I get the strain energy density of the material at two different states. So at the ultimate stress, it's called the modulus of the strain energy density is called the modulus of toughness. That'd be if I was pounding on the material or I impacted with something, I could compare the strain energy density of that impact or that whatever to the strain energy density at this point of failure, or which is also known as the modulus of toughness, and see if I meet or exceed that. And that'd be like a failure criteria. Something that's probably closer to home for us is more of the modulus of resilience, which is the strain energy density at yield. At the yield point, if you will. So if I could find how much strain, what the strain energy density being introduced to a material is, I can compare against an appropriate modulus and say, does it meet and use that as kind of like a failure criteria, the same way that we compared to shear stresses or ultimate stresses before. We cool with that idea? Sweet. All right. So let's play with that a little bit more. Yeah, we got that. All right. Oh, make sure I get that. Yeah. Yeah. Cool. All right. So make sure I do this correctly. So I'm not trusting what I wrote down for some reason. I want to make sure I got it right. Yeah. Okay. Okay. So like a first pass at this would be, say that we're dropping. Say that we're trying to plan for some unexpected failure, and the failure mode is that I have a block. Say that it's a support for support for something, either an engine or whatever. And something's, oh, don't fail on me now. and, and something's falling onto that block. All right. So there's some height involved. There's some mass involved. There's all kinds of stuff like that. Um, how would I find the amount of energy that this block could transfer to this support? Yeah, if it's just falling, all it has is gravitational potential energy. We'll say its original velocity is 0, so we don't have to care about any kinetic energy. So the total amount of energy that could be transferred What? Exford?
Yeah.
Yeah, well, is the total amount of energy that could be transferred is just equal to the gravitational potential energy, or mass times gravity times height. Yes. V naught equals 0. Yeah. If V naught was not 0, we'd have to add a kinetic energy term into this as well, right? But it's 0, so that goes away. Yay. Yeah. It said that's the total amount of energy that could be transferred. Why might it not be the total amount of energy that is transferred? Okay, so you could have more energy come into the system, but that's probably not going to happen.
Could hit it on the side and bounce off.
Okay, it could hit on the side and bounce off. Which part of that sentence would lead to not the full amount of energy transferring?
It's still have energy when it hit the ground beneath this support.
Okay, so if this guy hits the support and bounces, so like if I have this bouncy ball and I bounce it off the floor, it comes back up to a certain height, that means that some of the original energy that was in the system of the ball is still in the ball. It didn't all get didn't all get transferred to the point of impact necessarily. So that means that not all this would be transferred. What's the only type of collision where all the energy is transferred? Inelastic, right? When they stick together. So that's one kind of one major assumption here. This is the total amount of energy that will be transferred is actually the absolute worst case scenario. That may or may not be the case. You'd have to judge each thing by itself. For most everything that we're doing here, we're going to assume that all the energy is transferred, though. So you're safe. Congratulations. So that's such as something to keep in mind. We're not without assumptions here. We just have different assumptions than, say, the more impulse-related methods. Cool. So back to this. So we have some amount of energy here, some E initial mass gravity H. Cool. Where are we? Here we are. Yeah, tell me about it. I thought it was just doing better at this time at this time morning. And if I wanted to find, say, a total amount of strain energy, a total amount of strain energy here, I could do something like go back to why is this really confusing me right now? Okay, there we go. I could go back to our expression that we had before, which was integral 0 to x, that guy, which is just another way of saying that, right? Like, I can swap those out all day for a normal stress. Yes.
Is that within the whole curve, or is that just in the?
That's, yeah, right. This can only be done inside of the linear portion of the stress strain curve. But our failure criterion normally yield stress. So this is an okay assumption for us. However, it does mean that we cannot compare this. Well, we can, just wouldn't make any sense to compare this against a modulus of toughness, because modulus of toughness would be like looking at the entire curve. It'd be more appropriate for us to compare against the modulus of resilience, because that's only the yield portion of the curve. Okay, so if we had that, and we did the integral here, just as stated, get us like a 1/2 e epsilon x squared. Yeah, cool. And then if we wanted to, let's say, so how much strain energy, because this is like straight up energy, it's not like an energy density, right? So if we wanted to get this in terms of energy too, it was like how much energy like this would absorb due to some sort of axial load being caused by a brick falling on top of it. Well, if strain energy density is just strain energy divided by some volume, rather some, if you wanted to treat it in some differentiable and continuous way, some differential strain energy divided by some differential volume. So I think of this like strain energy density at an instant in time. We could say, well, got something like that. Also, are you guys cool with deltas for differentials? Okay, that's this just means that's the differential of u. You'll see it, you'll see them more when you start talking about partial derivatives and stuff. But it means the same thing as using a dy dx. It's just better form. Anyhow, so we got this, and if we integrated, integrating's the best game ever. Well, this side would be straightforward. Essentially, it's just from 0 to u. This side's a little bit more wonky because integrating by volume, I mean, something in here is going to change, right? But the question is what? So if we back that up a little bit, I'm going to need a little bit more room here. E epsilon x squared over 2 dv. Well, volume's just a cross-sectional area times the length, right? And cross-sectional area is not really changing by that much, but the length's going to be changing by more. It's going to be changing in a more significant way. So I can swap out that dv for something like an area times length, right? Cool. What am I missing here? I know I'm missing something. Oh, that's what I'm missing. That should be squared too, because his was what's called sigma squared to start out with. No, sorry, no, it shouldn't be. I'm being dumb. I integrated to get that. Sorry. All right. Where was I? I was there. Yes.
The reducing the constant.
Yeah. Yeah. Because we're assuming that the material doesn't change.
Yeah.
Yep. Seems like a decent assumption. Cool. What was I doing here? Crap. What was I doing? Sorry.
Where is the area?
We call, so this was volume, right?
Okay.
Yeah. Yeah, got it. ADM is pretty bad for me too. Where was I? Crappity crap. Okay. We get to there, right? Right. Okay. Cool. Okay, that makes sense. I'm on board now. All right. Right. We need to make that substitution in order to get to there, and that makes everything work out better. Okay. Right. Okay. Cool. Okay. So this gets us towards something that's maybe a little bit nicer, because since now we're integrating with respect to a length instead of a volume, and maybe we have something in here that can can help us get there. And the 0 to L would be like the total length of the support. If this was the strain energy density of the support, because that's what's absorbing all of the energy, then we're integrating it over the volume of the support itself. Yes.
So the line L should be in the parallel to line H.
Line L parallel to line H. No, because this is which all the reason H4 is to get the initial amount of energy carried by this guy. This guy can be going any direction that you want, as long as it sticks to the thing that it's hitting, right? This can get energy however it wants to, as long as we can figure out the amount of energy when it hits there. But what we are worried about is that its impact force being directed in line with the axis of the support for this present computation, because we're assuming that everything goes into creating an axial stress. Okay?
So, like, its impact should be in the same direction as L.
Yes. The impact should be in the same direction, but it can acquire the energy for that impact however it wants. Birds flying into it or otherwise.
Cross-sectional area A would be like going that way on it.
Like that? Yeah.
And then if it was going from the side, those things would be switched.
Yeah, got it.
Right.
Actually, if it was going from the side, it would create a bending in stress instead, and then we do a completely different derivation. Sweet, right? Okay, so we have this, but we can't integrate it yet because we don't have. I mean, we know that something in here varies with respect to x, but we don't really have an explicit relationship yet. So what we can do is say, well, E epsilon is a stress. So I can start doing some substitutions in here. And maybe I can get like maybe I can make some of these variables combine or go away and become some sort of a constant. So if E epsilon is a stress, I can say that, and that gets us a little closer, but I still have a strain in there. So if I factor out a modulus of elasticity, so if I do that, that's like legal tender. So that's like legal tender, right? I'm multiplying by 1. But because I have an E epsilon here, I can combine them and get a sigma x squared. So that was fun. We're getting closer here now. And hey, if I do the same thing with area, I have like an area squared, and if the stress is just a force over an area, especially a normal stress, then that means that this guy, if I go back up to the top, simplifies to something like a load squared divided by 2ae dx. And all of those guys are constants at an instant. So this one I can integrate from 0 to the length of the support. And I'll get something like p squared L over 2ae, which is the amount of strain energy produced by an axial load. And if I wanted to, I could say, well, that's the amount of energy that I'm going to be introducing to this system. That's the amount of energy that's going to be creating that axial load. I can kind of find kind of an equivalent force that would be created by an inelastic collision of these two objects. Isn't that cool? That's called and once I have the load, heck, I can get stresses, I can get strains, I can do all kinds of crap. I can do all the analysis that we just did for the last 15 weeks, 14 weeks. Scary, right? So if we can do this for axial loads, it means that we can also do it for bending loads, which is probably more to the point for us, right? Because we know how crazy bending loads can get. All right, so we start up from the same kind of point. So strain energy being integrated over a volume. Oh my goodness, land sakes alive. Don't do that. So strain energy being integrated over a volume. If we're saying instead of pure axial load, if say you have some cantilever beam and we have a block falling onto the end of that beam, it's going to create some normal stress, right? So if we wanted to find out how much strain energy is created by that normal stress, well, we know the relationship between what's called normal stress and bending, right? That's just like MY over I kind of thing. So we could replace that and get something like m squared y squared over 2ei squared dv. And if we played our game where we substitute in an ADX for volume, could say, hey, this is starting to look familiar. This is starting to look a little bit familiar here. Like we have that's the dAdx. You have like a y squared dA, and that's like a second moment of area, right? Dx. So we can simplify this guy down to make a substitution for m, saying that sorry, this is going to be 0 to L. This is L. The amount of force created by this object is some load P. So this, dang it, ran out of space. So that block creates some load P when it hits. It means that the bending moment that it creates here would be like PL, or if I'm doing the integral, be like P times some distance x, right? It's going to create a bending moment. So it's going to create some bending at each part of this beam. That's going to be P times some distance x away from the point of impact. So if I do all of these substitutions in that and simplify the thing down, eventually going to get something that looks like something that looks like that. And that one, there you go. And that one I can, if I wish I wrote down the final form from that, and that one I can integrate and get some final form that looks like that, which is the amount of strain energy in a cantilever beam because of some impact at the end of the beam. All right, we happy with this so far? And the upshot of this is that we can do similar things for shear stress. We can do similar things for torsion, for shear strain, whatever. And because of that, we can get relationships between the amount of energy of impacting objects or falling objects or even just static things. Like a lot of motors have rated power outputs instead of torques. We can get relationships between these and how things are going to deform and fail. So on Thursday we're going to talk a little bit more about this, especially this cantilever beam example. I hope to get into Castigliano's theorem, or how beams deform with this. And then I'm hoping to leave next Tuesday open for whatever questions you have prior to the final. Any questions? There will at least be some suggested problems. Yeah. Yes. I'm sorry. What did you say? It's a 6 times d times I. It's like you integrate x squared over 2, you get x cubed over 6. Yep. Yep. Yeah. Do you have someone? Okay. Cool. Yeah, cool.